Before we move to mass spectrometer, which is the third part of this video series, I just want to clear something that 4.20 times 10 to the power, this one here, times 10 to the power of 4 is not 42,000, but actually is 168 thousandths. And then this will result into a different value here. So it will be 2.52 times 10 to the power of 3 volts. I'm sorry about this confusion. And I hope that you caught it before this video, but even if you didn't, then now it's fixed. Okay, now we will move to mass spectrometer. Mass spectrometer is a device that is used to separate ions. Okay, what are ions? Let's recall it from chemistry. Sorry, isotopes, not ions, isotopes. Isotopes have the same atomic number, meaning number of protons, but different atomic mass, number of protons and neutrons. So they have more or less neutrons than what you see on the periodic table. This will result into isotopes entering into a reaction in the same way. So you cannot define if it is with a chemical reaction, if this is a carbon 14 or carbon 12. You cannot make that distinguish using chemical reaction. Therefore, in order to separate them, what do we use is the physical properties of isotopes. Having different masses, meaning that when they enter into a magnetic field, they will have, because remember what we said about magnetic force being equal to centripetal force. Magnetic force is QVB, so and centripetal force is mv squared over r, so v and v's cancel, and then we are ending up with QB is equal to mv over r. So if we have two different masses, because r is mv over qb, if the mass is changing, then the radius will change as well. If the mass is greater, then the radius will be greater. So what will happen is that when they are into a magnetic field, the accumulation of the isotopes will be different because of their masses, and if everything is kept the same. So lighter isotopes will travel in smaller circles in comparison to the heavier isotopes. So if we have here an isotope 1 and isotope 2, then mass of isotope 1 is less than mass of, not too much, too less, but less than mass of isotope 2. Okay, so let's see now a bit more about, I will bring a picture here and then we will talk about that. So this is a simplified version of a mass spectrometer. What do we have here is we have 3 sections. The first one is the acceleration. The second one is the velocity selector. And the third, so first one, second one is the velocity selector, and the third one is the separation. So what is happening on the first one is that we have material that is pulverized, and then through the plates that have a difference of potential energy, the charges are accelerated. Why are they like this? Because the kinetic energy is increased by the transformation of the electric potential energy. So kinetic energy is equals to QV. We discussed this when we did the parallel plates. A charge entering into parallel plates in the same collinear with the electric field. Okay, you can refer to that video if you are still having difficulties on or understanding. On the second part is what the velocity selector is. So what the velocity selector is, as ions are passing through the accelerator opening, they are entering into the velocity selector. Okay, what it is doing, the purpose of the velocity selector is to select the certain velocity based on the ratio between the electric field strength and magnetic field strength. And the charges are going undeflected. So what is happening on this case is that only the ions that have a certain speed that is equal to the electric field over the magnetic field that is between those, or it's merged with those two parallel plates. And what is happening on the third part, which is, so this is velocity selector. And here we have accelerator. And what we have on the third part is separation, ion separation. So what is happening here is that magnetic force, because we have only magnetic force now, magnetic force is equal to centripetal force, or QVB is equal to mv squared over r. So these canceled out, and then we have radius of mv over qb. So now ions that are different isotopes of the same element are entering in this magnetic field, and then as a result of the difference of masses, so they will be accumulated in different areas. And this, just to clarify, it is B2. So this is B2. Okay, so this is the principle that mass spectrometer has, and it's a very simplified version of the mass spectrometer. We will do an example, have an example of different isotopes and what is the radius of each of them. This is a very long example, so what I will do is I will copy and paste it here, and then we can work with it. Just an advice, when you see a question like this, that it's a lot of information on it, do not be overwhelmed. Just skim through it and then figure out what is that you are going to find, and select the information that you have from the question, and just use your brain, use the logic, and figure out what they are looking. So in this question, we are dealing with isotopes of uranium, and there are two of the forms of the isotopes is isotope uranium-235 and uranium-239, which means that you have 239 and 235 into that, as a particle, can be separated using mass spectrometer. Uranium-235 travels through a small circle and can be gathered at a different point than uranium-239. So it is simply the principle of mass spectrometer that we have talked with. And this is what I suggest you doing. Go there, read the question, and then say, oh, where does this belong? Mass spectrometer. And then flip the page in your brain, boom, 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 mass spectrometer. During World War II, the Manhattan Project was attempting to make an atomic bomb. Useless information for those purposes. Uranium-235 is feasible, but it makes up only 0.70% of uranium in Earth. A large mass of uranium mass spectrometer at Oak Ridge in Tennessee was used to separate uranium-235 from raw uranium metal. We know that because it is mass spectrometer that we are dealing. But this is what you will see on the question, okay? So don't be overwhelmed. Uranium-235 and uranium-239 ions each has a charge of +2, with a charge of +2 directed into velocity selector, this one here, which has a magnetic field of 0.250 Tesla and an electric field of 1.35 times 10 to the power of 25 times 10 to the power of 7 volts per meter perpendicular to each other. The ion then passes into a magnetic field of 2 millitesla. What is the radius of the deflection of each isotope? So as I said, like a lot of information, and I'm giving this question so that you are aware of things that you will see on the diploma. Okay, so now let's select and gather the information that we need from those wordy questions. Okay, so charge, so we'll start here. Charge is +2, okay? Charge means that +2 elementary charge, or +2 times 1.60 times 10 to the power of -19 coulombs, which is 3.20 times 10 to the power of -19 coulombs, okay? Now, since we are dealing with the mass, so mass of 235, or isotope form of the uranium, is 235 times 1 point, because mass of proton and neutrons is pretty much the same, 1.67 times 10 to the power of -27 kilograms. So this will be 3.9245. I will keep all those numbers, times 10 to the power of -25 kilograms. And mass of 239 will be 239 times 1.67 times 10 to the power of -27 kilograms, which will be 3.9913 times 10 to the power of -25 kilograms. Okay. So this is the information that we gather from the question. Now, on the velocity selector, what is happening? So velocity selector, what is happening is that electric force is equal to magnetic force, or EQ is equal to QV, and this is V1, okay? Because refer to this question, this picture here, V1. Okay, so now V1 is, let's read the question, has a magnetic field of 0.250 Tesla, okay? So Q is cancelled first, and then V will be E over V. So B1 will be 0.250 Tesla. And then let's go back to the question again. And an electric field of 1.27 times 10 to the power of 7. 1.25, not 27, times 10 to the power of 7. and this is volts per meter. When you enter this in your calculator, what you will see is that the velocity of the ions that are selected to go to the ion separation is 5.0 times 10 to the power of 7 meters per second. And now the ions are entering into the ion separation, ion separator. As they are entering in the ion separator, magnetic force is equal to centripetal force, or QVB, and in this case will be B2. Refer to this like graph here, simplified version of mass spectrometer. B2 is equal to mv squared over r. So v is cancelled out, and then we find that r is equal to mv over qb2. Now we have two ions. When we have uranium 235, then the radius of 235 uranium will be mass of 235 times velocity over Q of 235 times B2. So we found mass of the 235, which was 3.9245 times 10 to the power of negative 25, velocity of 5.0 times 10 to the power of 7 over charge. We said that they are all 3.20 times 10 to the power of negative 19 times the magnetic field strength in the ion separation is 2.0 millitesla, which means that is 2.0 times 10 to the negative 3 Tesla. And when you enter this in your calculator, you will have a radius of 3.07 times 10 to the power of 4 meters. Now, what are you expecting that the radius of uranium 239 is going to be greater or less than 3.07? I'm assuming that all of you are saying greater, because the mass of 239 is greater than the mass of 237. And since everything else is kept the same, then the radius of 239 will be mass of 239 times velocity over charge of 239 over R2. So it will be 3.9913, which we found up there, 5.0 times 10 to the 7 over 3.20 times 10 to the negative 19 times 2.0 times 10 to the negative 3. So the radius of uranium 239 will be 3.12 times 10 to the power of 4 or negative 4 meters. It is 4 meters. So this is how you deal with the mass spectrometer questions. Just keep in mind the principle that mass spectrometer has. So you have acceleration area, part or section, and then you have velocity selector section, and then you have the ion separator section. So on each of them, with the principles that we use, we have done parts of it, and through the forces and fields. We have on the first one, we are using the fact that the charge is moving parallel with the magnetic field strength after it is ionized, meaning that a charge is formed, and that is formed through pulverizing. And then as it is accelerating enough, it is going through the velocity selector, which the objective of velocity selector, or the job of a velocity selector, is to select the charges with a certain velocity, and it's a combination of the perpendicular electric and magnetic field, and then we are calling it B1 here. And then the third part is ion separator, in which the undeflected ions are entering into presence of the magnetic field, B2, and since they have different masses, but everything else is the same, they are obtaining different radius, and therefore the separation of the isotopes is happening. And as I said at the beginning of this video, this is because the isotopes in a chemical reaction react the same. You cannot separate isotopes using chemical properties, so therefore we use physical properties of the isotopes. I hope that this makes sense. We will discuss more about this in class, and if you have any question or anything, then let me know.